Okay, now this session is now being recorded. Welcome to 4025 MAA Mechanics tutorial number 2. Second week, we dealt with loads and equilibrium last time. So all these tutorial questions will be about equilibrium of bodies. So we want, for the first question, we want to determine the forces in cables AC and AB. So AC and AB. Needed to hold the 20 kilogram ball D in equilibrium. We also know that there is an external force acting, an active force of 300 Newton horizontally, and this distance D is 1 meter. So how do we go about that? We have to do the free body diagram of something. So what do we start from? So where do we start from? Free body diagram of what? So to find the cable tensions, we need to cut. Yeah, so do the free body diagram of the ball. So ideally you want to cut here. Now you can do the free body diagram of the ball first. Let's do that. So you want to cut here and have the ball like this. So how many forces are acting here on the ball? 2. That would be the weight of the ball in red. This would be the weight of the ball, mg, and of course the tension AD, the tension on D from A, so TDA. And assuming that we have a y-axis pointing in this direction, what is the equation for this ball? So let's have x, y, and z. Let's call this the center of gravity G of the ball. So what's the horizontal equilibrium? The equation of equilibrium, horizontal equilibrium, we have sum of forces along x equals 0, sum of forces along y equals 0, and sum of moments around G equals 0. Now, of course, this first equation here, you should agree with me, this equation here is 0 equals 0. So we don't have anything to show. So if I redo this, I put it here, I get that this first equation is 0 equals 0. So it's a useless equation. It doesn't tell us anything. And we know that TDA minus mg equals 0. TDA is positive because it's according to the y-axis. mg is negative because it's opposing the y-axis. Okay, so that depends on how you choose your axis. If you had chosen your y-axis going downward, this equation would have been inverted, would be mg minus TDA, but it's the same thing. It's the same equation. You just have to, if you multiply everything times -1, you still get the same equation. Now, what's the equation of moments? What's the moments equation? Remember, this is translation x, this is translation y, and this is rotation around z. That's the idea. So what's the moment equation around G? Come on, chat. 0. What's 0? Shut up says 0, but can you please explain that 0? What do you mean with that? Do you mean 0 equals 0? Yeah, there is no moment. There is no moment because both of these forces are passing through G. See, TDA and mg are passing through G. That means this equation is 0 equals 0. So the only equation that we care about is this one. And this equation just tells us that TDA equals mg. So how much is mg? This is 20 kilogram ball. So mg is, let me see if I can do this. Mg is 20 times 9.81. It's 196.2. So TDA is 196.2 newtons. So we know this. Nice. Now we do the free body diagram of the hoop A. See, in A, we have this hoop, this one. And we need to do the free body diagram of this. So that means we have to remove it from the system. So how many forces are acting on A? This is the hoop A. How many forces are acting on A? You say 4, that is correct. So we have one active force, F. We have one force here, which is the tension of the cable, TBA. And this is one other tension, that is TCA. And this is the force. Now, which direction is TDA? Is TDA going upward or downward? So it looks like TDA is going upward, but here we must take it downward. Okay, so this is TDA. Also, this I changed. So let's change this, because I used annotation here. This is the tension on D from A. So this is on A from B, this is on A from C, and this is on A from D. Okay, so TAD must be equal and opposite, all right? Because this hoop feels brought down by this sphere, and this sphere feels propped up by the hoop, okay? Does it make sense? Good. Now, do we know the angles? Because what happens here is that this TAB has got an horizontal component and a vertical component. And this TAC also has an horizontal component and a vertical component. So we must be able to split both of these into components. But in order to do so, we need to find what are the triangles. Now, I might argue that this triangle here is what we need. Okay, so this is one angle. Let's call this alpha. How much is alpha? So trigonometry. We have this triangle here. This is the alpha that we want. We know that this is D, and this is 2 meters. So, okay, so alpha, remember this is point A and this is point C. So alpha is the arctangent of opposite divided adjacent, which is D divided by 2, which in our case, D is 1 meter. So it's arctangent of 1/2, and that means the arctangent of 1/2 should be 45 degrees. No, arctangent of 1 is 45 degrees. So 0.5 arctangent, that's tangent minus 1. It's in degrees to 26.57 degrees. So this is equal to 26.57 degrees. All right, so we know alpha. But we have another triangle here. Let me put this in red-ish. So this is the other triangle that we need. So we want beta, this angle here, this is beta. So how do I find beta? Well, let's draw the triangle again. Now this is just taller triangle, the same base. So this is still 2. Now this is D and 1.5. Yeah. So remember, this is point A, this is point B. So that means that this angle here that I called beta is arctangent of, so arctangent of opposite divided adjacent. Opposite is d plus 1.5 and adjacent is 2. So this gives 2.5 divided by 2. So 2.5 divided by 2, 1.25. Arctangent of that is 51.34 degrees. So we know beta and we know alpha. And we know that TAB, this angle is beta. And for TAC, this angle is alpha. All right. Now, very easy. We can split TAB and TAC into components. So TAB x. Now let's write the equations of equilibrium. So the horizontal equation is minus TAB x minus TAC x plus F equals 0. We haven't split them yet. We just labeled them TABX and TACX. In the y direction, we have TABY plus TACY minus TAD equals 0. And of course, since all the forces are passing through the same point, there are no moments, so 0 equals 0. Okay, I write it anyway, even if I don't use it. And now we can explicitate the first two. So now explicitate the components. So I have x and y now. I'm not using the third equation because it's useless. And so this is minus TAB cosine of alpha. How do I know? Because TAB is this one. And this is adjacent. Okay. Sorry, TAB. So it's not alpha, TAB is beta. Yeah, my bad. So it's this one. TABX. So cosine beta. And minus TAC cosine of alpha, because we are looking at this one. And then we have plus F equals 0. And then we have TAB sine of beta plus TAC sine of alpha minus TAD equals 0. There you go. Now, how many unknowns we have in this system here? TAB is unknown, TAC is the second unknown, F is given, this one is given. It's 300 newtons. TAB is the first unknown, TAC is the second unknown, alpha and beta we found here. These are just numbers. TAD was 196.2. Remember, TAD and TDA are equal and opposite. There you go. So it's two equations, two unknowns. So solve two equations, two unknowns. And we end up with TAB equals and TAC equals. Now, TAB is 98.6 newtons according to the solutions, and TAC is 267 newtons. Do you know how to solve systems of simultaneous equations? Please answer me honestly. Okay, yes. Anyone else? Please answer honestly. Okay, yes, good. Because if you cannot, or if you struggle with this, we have a Sigma support center. That's how it's called, but Sigma means that we give you mathematical support. Okay, so just basic mathematics support. So everything, trigonometry, systems of equations, algebra, simplifications, anything that has to do with basic math, we can give you support in the library. Okay, in the library, if you are an online student, you can ask for an online support, of course. Just go to the student portal, search for Sigma Center or Sigma Support session, something like that. If you look for Sigma, you'll find it. Okay, that's it. Very easy. How was this? Complicated? Hard? I think that was easy. Okay, so this is question 1. And we solved it. Now we have question 2. This one here. Yeah. Let me put these down. Let's see if we have time to solve them later. So for question 2, we want to determine the mass of each of the 2 cylinders, so this one and this one, if they cause a sag S of 0.5 meters when suspended from the rings at A and B. And also note that S, this sag, there is no sag, of course, S is 0 when the cylinders are removed. So we have the undeformed lengths of the spring that we can find, and we also have the deformed lengths of the spring. That's the idea, okay? So this shaded, this semi-transparent drawing shows you the undeformed position of the springs. Okay, so what do we need here? How many free body diagrams we do? The mass is equal, right? Yes, why? How do you know that the mass is equal? It is correct. Shut up, the mass is equal. The mass of these 2 cylinders is the same, but can you tell me why? I mean, it's intuitive, but can you explain that intuition? Look at the system. The angle is the same. So yeah, the idea what happens is that this system here is symmetric. So we have a symmetry of the system. So since we have a symmetrical system that is symmetrically loaded and geometrically symmetric as well, there is no reason why forces should be different on here and here. So everything that happens on the left-hand side happens on the right-hand side as well. Okay, so we don't need many free body diagrams. We can only take care of 1/2 of the system. That's exactly what I'm going to do. So I'm going to use just the left-hand side and completely forget about the right-hand side. So let's see what happens. Let's do the free body diagram of A directly. If I do the free body diagram of A, what happens? This is A. Let's draw it here. This is point A. This is the hoop. And so how many forces does A feel? Two. Which ones? So there's the weight of the cylinder, of course, mg. Mario says 3. So do you agree with Mario or do you agree with shut up? What do you think? And we have this one, which is the spring load, as you said, Fk. Sam also says 3. So what's missing then? Is there which other force? All right, there is a force here on the right, because since we are looking at half of this, there's a cable here. Okay, so we must consider that cable as well. So if you cut here, A feels a force from the cable. Let's call this T. Let's call this T. That's it. Okay. So we don't know many things apparently. We don't know T, we don't know Fk, we don't know M. So the mass is unknown because that's what we want to find, to determine the mass. The tension is unknown because it's an internal force here that's not explicited anywhere. And the spring force is unknown. Is it unknown though? I believe we have enough information for the spring force to be completely known, okay? Because we have the original length of the spring and the new length of the spring. And so we also know that the springs have a stiffness of 100 newtons per meter. So as a reminder, I'm giving you that Fk is equal to minus Kx. Okay, let's call this minus Ks. And let's not call it S because S is here. Let's call it delta S. There you go. Or delta L, even easier. Apologies, guys. It's the same thing. Let's call it minus K delta L. So we have to check. We know K is given here. So 100 newtons per meter. But we also know delta L. This delta L is given in the form of the final length of the spring and the initial length of the spring. So as you know, delta L is the final length of the spring minus the initial length of the spring. So LF, L final minus L0. So I'll put this with a gray background so that to say that this is information that you should already know from the lecture. So this is like a formula sheet that you need to always have, always remember. Okay, so this is the free body diagram. We put it here. We also need to know the angle. Okay, so let's find the angle first. Remember, we need the angle because this has an horizontal component and a vertical component, so Fkx and Fky. So we need to find the angle. What's the angle? This angle, alpha. How much is alpha? Well, alpha is this triangle here, which is the hypotenuse of this. Now we have this one, and we have this one. So this is alpha, and this should be 90 degrees. There you go. This is 90 degrees. This is alpha. So how much is alpha? Come on. So trigonometry. Alpha is, well, it's 45, but why? Why you say so? Oh yeah, it's 45 because it's 2 over 2. But ideally, alpha is the arctangent of opposite, which is this one, 1.5 plus S, and S is 0.5. So it's S plus 1.5 divided adjacent, which is adjacent is 2. This thing here is this. Agreed? So in this case, this is arctangent of 1, and arctangent of 1 is 45 degrees. So yes, correct. Sum. There you go. Done. Easy. So that means we just have to find now the original length, so the final length and the original length. Now the final length is this one. And we know this edge. We know this edge. We know this is 2. This is 2. So we can say that the final length, come on. Now that the final length equals the square root of S plus 1.5 squared plus 2 squared, which in this case is 2 squared plus 2 squared. And it's the square root of this. So 4 plus 4 is the square root of 8, which is 2.83. 2.83 meters, that's the final length of the spring. And the original length of the spring is the square root of, so this, we are looking at this one now, this one. And we know that this is still 2, and this is 1.5. Okay. So this is 1.5 squared plus 2 squared equals 1.5 squared plus 2 squared equals under square root 2.5. So let's write the equilibrium equations. So equilibrium equations. Again, I'm not going to bother doing the moment equation because all these are passing through A. So equilibrium along the x-axis and equilibrium along the y-axis. Let me clear that the y-axis is this one and the x-axis is this one. And so we have minus, so we have T minus Fk x equal to 0. And we have Fky minus mg equal to 0. Now let's split this into components. So let's explicitate the components. Explicitate components. So this one becomes T minus, of course, Fkx is Fk, no, Fk, remember, is K delta L. So K delta L cosine of alpha equal to 0. And Fky is K delta L sine of alpha minus mg equal to 0. Okay, we have everything here. The two unknowns are T and M. So since we only want to find M, we don't care about T. We don't care about this one. We only solve equation 2. Solve 2 to find M. So that means that M, the mass that we want, equals K delta L sine alpha divided by G, which is still equal to K L final minus L original sine alpha divided by G, which is equal to, ideally, 2.37 kilograms. Let me check. So we have K is 100 times 2.83 minus 2.5, 33 times the sine of 45, 23 divided by 9.81, 2.37 kilograms. There you go. Okay, any questions, guys? What do you think? Was this easy or not? I mean, you had to think about it geometrically, but it wasn't too bad, I believe. Any questions? No, sir. Okay, no questions? Good, so let's delve into number 3. Oh, one thing I want to advise is don't put numbers in. See, I don't like to put numbers anywhere. I always use letters all the way through. Even if I found LF and L0, I still use them until the very end. Because what happens is that you might discover things. Okay? All right. So question 3, I believe, is this one. Okay, let's get size number 3. So let me put this down. Down. Okay, let's add another page. Can I add another page? Okay, it's fine. Let's do this. Okay, that's another page. This is question 3. The horizontal beam is supported by spring at its ends. Each spring has a stiffness of 5,000 Newton per meter. So 5 kilonewtons per meter means 5,000 newtons per meter, and is originally unstretched so that the beam is in the horizontal position. So this, what we are witnessing here is the unstretched. So this is the position before deformation. Now, if we apply an 800 newtons load here at point C, which is not in the middle, so it's 1/3 of the way across the beam, we want to determine the angle of tilt that this force causes, because of course, as you might imagine, if this was exactly in the middle, so if this load here was exactly here in the middle, this would be a symmetric problem, exactly like before. So you would have the same reaction force here and here, and there would be no tilt. Because why would it be tilting one way or the other? There would be no reason to tilt. Now, since this is not applied in the middle, it's applied 1/3 of the way. So this is 1/3, so it's 1/3 of the way. That means that this spring will feel more of this force, and this spring will feel less of this force, so they will react differently. So this will react more, and this will react less. And it's up to you to find how much they react. Once you know the reaction force of this spring, you also know that since it's due to a spring, this also applies. This also applies. Let me put this here so we have it ready for use. Yeah. So once you know that the reaction force is a certain value, you can also know how much deformation this has caused to the spring. So let's start by doing the free body diagram of what? So what is the free body diagram that we need to do? Is the beam massive? Does it have mass? Doesn't seem like so. So how many forces are acting on this beam? Come on, how many forces? 3. Okay, that is correct. So 1 is the active force of 800 newtons. Let's call this F. See, even if you have numbers, I still like to use letters because I want to see the relationship between these numbers. And I know that this is L. Let's call this capital L. Let's call this, because L is the length of the spring. Let's call this B. Small b, and let's call this small a. Okay, we know that small a is 1, b is 3. The other two forces are the reaction force at A and the reaction force at B. Why did I put them upwards? Can I say that they are downwards? I mean, the idea is that these reaction forces are completely unknown. We don't know them. So what I'm doing here is I am assuming that this is going upwards, and I am assuming that this is going upwards. If my assumption is correct, I will get a positive number for RA and a positive number for RB. If my assumption is incorrect, I would get a negative number. If I get a negative number on a reaction force, that means that my assumption in the direction of the force was incorrect. Okay? Good. Now I know, well, this is the active force is this one, so the two reactions must be opposite to that because they want to oppose the active force. That's the idea. So how many equations I need? Do I need all three equations? Equilibrium equations. You all say we need three. I disagree, but let's check. What are the equilibrium equations? Well, in 2D, remember, the real equilibrium equations are sum of vectorial forces equal to 0, sum of vectorial moments about a point equal to 0. So these are the equilibrium equations, always valid, always there. These are the fundamental equations of statics. Of course, this equation here can be split into its x component and y component because it's a vectorial equation. And in 2D, this equation is a single equation because you can only rotate in the z plane, so about the z-axis, so in the xy plane. So that's why we wrote three equations, but do we need all of them? Okay, I see that some says no x is needed. That is correct because we don't have any horizontal force. If I use, of course, you always have to tell me which one is x and which one is y, because if you don't tell me, I don't know what to put in the x, what to put in the y, because if you call this y, then we don't need the y equation. Depends on how you call them. So since we are sticking to the convention that the x is horizontal rightward and the y is vertical upward, in this case, we don't need the x direction components because there are no components, no forces in that direction. What about y? Yes, that's easy. We have minus 800. So let's do RA plus, let's do them in order, 1, 2, 3. So RA minus F plus RB equals 0. Positive because it's according to the y-axis, negative against the y-axis, positive according to the y-axis. And so, well, problem here is that we have 1, 2 unknowns in a single equation. So we can't solve this equation yet because we have 2 unknowns in one equation. So that means we need to choose a point for the sum of moments about a point equal to 0. Which point? Which point? Any point? Some says A, Kalechi says A. Why A? Any particular reason why A? Some says to cancel RA. That is a very good, argument. So I would also choose A because, I mean, there are no wrong points. So you can take any point, remember, some moments about P, but there are smart points and dumb points to take. So smart points and not so smart points about which to take the moments. If I take the moment about this point A, remember this is A, this is B, this is C. If I take the moment about A, RA gives no moment about A because it's passing through A. So we only have to take care about F, the moment of F about A, and the moment of RB about A. So how much is the moment of F about A? Remember, what is the moment of a force about a point? Force times perpendicular distance. So what is the moment of F about A? Write it down in the chat, please. The moment of F about A. Come on. F times small a. It's not just F. It can be just F because, okay, I see what you did because A is 1 meter. Yeah, but it's not just F, because if you say just F, you are telling me that this moment is measured in newtons, which is not correct. Okay, so F times 1, it's still, the magnitude is F, but it's Newton meters. So it's still F times 1 meter. Okay, so don't be misled by these things. So we say that this is it positive or negative? So remember, X over Y, this is the positive moment direction. So is F about A a positive or negative moment? Well, some says negative moment. I do concur. So F around A rotates clockwise, and clockwise is C against my positive direction. So that means it's minus F times A. So we have to add RB. What is the moment of RB about point A? What is the moment of the force RB about point A? Help me out. Come on. Help me out. Come on. Force times perpendicular distance. So the force is RB times B, small b. Positive or negative? What do I put here? Positive or negative? Some says plus, and I do agree because RB around A is counterclockwise around A. So positive RB times B. And that's it. That's equal to 0. Now look at the magic. This is the only unknown because F is given. F is a number, A is a number, this small a is a number, small b is a number. This is the only unknown. So just for sport, let's write the same moment. So let me put this here in a very clear color, in a very different color. So let's do the sum of moments about C equal to 0. This equation here would look like, so about C, that means this gives no moment, RA gives a negative moment, and RB gives a positive moment. So what we'll have is RB times this distance now, and this distance is B minus A, plus, negative, minus RA times A equals 0. Now see, this equation here is much harder than this equation here. Do you agree with me? Because here we have two unknowns as well. We still have two unknowns. That's why I'm saying there is a smart choice and there is a not so smart choice. Okay, the equation is fine. You still get the same number in the end, but this is not very smart. So not a smart choice. Let me put it here, not a smart choice. Although the equation is completely correct. All right, so we can now find very easily solve equal, let's call this equation 1 and this equation 2. And I say solve equation 2 to find RB. Then I get that RB is just FA, F times A divided by B. That's equal to where A is 1, B is 3, F is 800, so it's 800 divided by 3. It's 266.67 newtons. Easy. And now that I know this, I can easily find RA, solve 2 to find RB, and then finally 1 to find RA. So this is equation 2, this is equation 1. And from here, I say that RA is just F minus RB. And so that must be, of course, it's 800. This minus 800, so it's 533. I have to change sign to this, so it's 533.33. And it must be because the sum of these, so this plus this must cancel this. That's the idea. Okay, is this the end? Of course it's not, because we still haven't scratched the surface of the, we just scratched the surface of the problem. Because now what happens is that these forces, both of these, come from springs. Okay, so this one and this one. Therefore, we can use Fk equals minus K delta L to find the elongations. Well, let's say, call them deformations. Delta L of spring A and delta L of the spring B. But that's very easy. So we know that RB equals K minus K delta LB. Therefore, delta LB is RB minus RB over K, which is equal to the spring stiffness is 5,000 newtons per meter. So it's 266.67 newtons divided by 5,000 newtons per meter. This gives an elongation of 0.05 meters. So if I times this times 1,000, this gives 53.3 millimeters. And for RB, so for RA, that's exactly the same thing. So delta LA equals minus RA. So this is negative, okay, because the spring is in compression. So it's negative 53.3 millimeters because it's in compression. Minus RA divided by K is, let me see, do this. It's 533.33 divided by 5,000. This times 1,000 is 106.7 millimeters negative because it's also in compression. So as you can see, delta LA, so spring A deforms more, so compresses more, and spring B compresses almost half as much. That means that the final thing looks like this. This is A, and this is B. All right. So what's the angle? What we want to find here is this angle here, alpha. So how do we find alpha? Opposite divided adjacent. Opposite is this, O, and adjacent is, we called it B. Okay, so let's call this D. So what's this distance D? This goes down. So this was the original bar was here. The original bar was here. This has gone down by delta LA. This has gone down by delta LB. So how much is D? How much is D? Oh, delta LB minus delta L. It's delta LA minus delta LB, the other way around. Okay, it's this minus this. If I put them side by side, I get this is delta LA, this is delta LB, and this is D. Okay, agreed? So I get that D is delta LA minus delta LB, which is 106 minus 106.7 minus 53.3. This gives 53.4. We need the absolute value because it's a distance anyway, so we don't care about the sign. So 53.4. There you go. Alpha equals arctangent of opposite divided adjacent, D over B, which is equal to 53.4 millimeters, of course. 53.4 divided by 3 meters, which is 3,000, because we are using millimeters here now. So 53.4 divided by 3,000 equals 53.4 divided by 3,000. Arctangent of this, it's 1 degree, 0.02. Yeah, 1.02 degrees. There you go. See, that's the answer here, 1.02 degrees. Okay, I don't think there's time to solve this one, but this one is quite easy. Okay, I will give you how to start the tutorial. So ideally, what you want to do here is if cables B and D, BD and BC can withstand a maximum tensile force of 20 kilonewtons, determine the maximum mass of the girder that can be suspended from cable AB so that neither cable will fail. The center of mass of the girder is located at point G. Now, ideally, what you want to do here is that you know that the forces, let's do the free body diagram of B. Then you have FAB FBC and FBD. And the other free body diagram that you have to do is the free body diagram of the girder itself. And this is FCB and FDB and the mass mg. Okay. So this, you don't know anything about this yet. So you have to make sure that you start from here. And it says that these cables can withstand a maximum tensile force. So since you don't have much information, you can say, if I assume this is 20 kilonewtons, then you can solve it. But if FCB comes greater than 20 kilonewtons, your assumption is wrong. Because remember, these can withstand at most 20 kilonewtons. So if you assume that this is 20 and this is more, well, your assumption is wrong. In that case, you assume that this is 20. And of course, this must come smaller. Okay, so up to you. I can give you a prediction. My prediction is that the most vertical cable, which is this one will reach 20 kilonewton first. Okay. That means that if you assume that this is 20, this is the correct assumption. But again, don't let my prediction point you in a certain direction. I want you to try and explore the problem yourselves. All right, any questions? We are already 2 minutes over the time, so I will take a last round of questions if you have any. Do you? No questions? Doesn't seem like so. So let me stop recording. You should want to stop recording? Yes.